Your test is basically me controlling every aspect of the experiment.
Yeah. Okay, let's get started. I'm going to introduce the speaker for the rest of the day. And the next talk is going to be by Anup Rao. Anup is now a postdoc in Georgia Tech working with CentOS. Before that, he actually completed his PhD in math with Daniel Spielman in Yale University working on graph algorithms. Today he's going to talk about robust estimation of mean and covariance. Okay, let's just...
Thank you. Okay, so before talking about robust statistics, let's consider a classical estimation problem. Suppose we are given samples from a 1D distribution, say 1D Gaussian, and we want to estimate its mean and variance. Can we do it? And the answer is yes. We can use sample mean and sample variance. And this is the maximum likelihood estimator for this problem. And probably a century back, Fisher proved that maximum likelihood estimators are optimal in a certain specific sense. Later, Tukey asked, what if there is error in the model? This resulted in a whole field called robust statistics. And there are many books now written in this field. And the central question studied can be summarized as how do estimators do well in a neighborhood of the model? Let's consider the 1D example again. Suppose we have Gaussian samples, but now corrupted by some noise. Can we accurately estimate mean and variance? Before answering that, we need to constrain the noise somehow. There are many ways to do this. One natural way is we let an adversary add eta fraction of points. This was initially suggested by Huber and also studied in robust statistics literature. More precisely, suppose we have m points. 1 minus eta fraction are independently sampled from an underlying distribution, and eta fraction of them are chosen by an adversary. Adversary can look at the samples from the distribution before choosing the points, which is a slight strengthening of Huber's contamination model. And now we would want to estimate mean and covariance. For this talk, what I mean by estimating mean and covariance is we want to estimate a mu hat, which is close to mu in 2 norm, and a sigma hat, which is close to true sigma, the covariance matrix, in the Frobenius norm. Before going into the details, just some applications, talk about some applications. Principal component analysis is a widely used tool for various learning tasks like clustering, dimensionality reduction, in learning Gaussian, in mixture models, independent component analysis, where usually people compute the top k principal components, where k is a constant, and project the data onto this space. But even if there are 2k corrupted points, the top k principal components can be completely off. So we'd like to estimate the covariance matrix in the presence of noise. Coming back to the 1D case, 1D Gaussian, does empirical the sample mean and variance work in this case? Just if you think for a bit, you can convince yourself that this will fail badly. Even if you have one noise point placed far away from the true mean, the sample mean can be arbitrarily bad. But in this case, there is an easy fix. If you look at median, that's a good estimator of the mean in the presence of noise, and you can show that this is optimal. And for the variance, you can use what's called median absolute deviation, which is the median of the distances of points from the median. So now the real question that we'll address in this talk is what about in higher dimensions? There have been several approaches suggested in robust statistics literature, and most of them are motivated by higher generalizations of median to higher dimensions. So I'll give a table in the next slide. So for the rest of the talk, M will denote the number of samples, N the dimension of the data, and eta is the fraction of the noise. So here is a list of approaches that have been studied. And the key thing to note here is either the error has a polynomial factor in the dimension, or the estimator is NP hard to compute in general, or it's exponential time to compute in general. So 2-key median has optimal performance. It is a generalization of median to higher dimension, but it's hard to compute in general. And geometric median, which has an efficient algorithm, has a square root and square root dependence on the dimension. So then the question is this all we can do? This robust statistics has existed for many decades, and until like a year back, this was the kind of status where either we have a very computationally expensive algorithm or a polynomial dependence on the dimension in the error guarantee. So thankfully we have an answer which it need not be the case, where there are now efficient algorithms which have good error guarantees. And let me state the results here. So I should say that this appeared in Fox 2016 along with Elias and his co-authors. Another paper appeared written by Elias and co-authors. And since then there has been a lot of work in this, and I won't be talking about them, but you'll see many of that in the next talk. So we would need, the algorithm will work, we need some assumption on the distribution, and the distribution for us has to satisfy what's called bounded fourth moment. That is, in any direction, the fourth moment should be at most C4 times the second moment square. The error guarantees can be parameterized in terms of C4, but for this talk I'll assume C4 is some constant. And many general classes of distributions satisfy this property. If a distribution has finite fourth moment, then this is obviously true, and sub-Gaussian, sub-exponential, and many other distributions satisfy this. So here's the main result. So if we know the covariance matrix and we want to estimate the mean robustly, then we can compute a mu hat such that it's at most eta power 3/4 times sigma square root log n away. So the thing to focus on is that the dependence on the dimension is square root log n instead of the usual square root n. And we have a lower bound of eta power 3/4 sigma in this case. So I should say that all the results I'll state will be with high probability. So it will hold with 1 minus 1 over poly n probability. Also there's another stronger noise model that people consider, where an adversary can delete some points and add some noise points. And even in this case, the results hold, though when we wrote the paper, we were not looking at that model. In the case of unknown covariance, the dependence on eta is like square root eta instead of eta power 3/4. Otherwise, the dimensional dependence is still square root log n. And in both these cases, the sample complexity is nearly linear, which is almost n log square n over eta square. And before going into the next slide, I should point out that in the case the distribution is Gaussian, then we can improve this eta power 3/4 to eta. And I'll sketch a proof of that later on. If you want to estimate the covariance, we use essentially the same algorithm as estimating the mean. Main thing to note is that if, say, the mean is 0, then covariance is expectation of XX transpose. Now, so that's the mean of XX transpose. So if we write down XX transpose as a vector and apply the mean estimation algorithm, then we can get this guarantee, which is we can, in Frobenius norm, get square root eta log n 2 norm of the covariance matrix. And since we are applying the mean estimation algorithm to second order objects, XX transpose, we'll need a slightly stronger condition, which is 8th moments. We need bounded 8th moments and 8-wise independence. So for the rest of the talk, I will focus on mean estimation algorithm, and also I'll assume the underlying distribution is Gaussian with noun covariance. Before jumping into the Gaussian case, I just want to point out that in the case of bounded fourth moment, even in one dimension, its median doesn't work. So here is a simple distribution with mean 0. It's concentrated on just 2 points. Even without noise, the median doesn't work if we have odd number of samples. But there is a simple fix. You can compute the an interval of length, smallest interval, which contains 1 minus eta fraction of the points, and compute the sample mean. And that will be we can show that as a good estimator. And though the algorithm that I'll state in the remaining slides will be for Gaussian, this is the main switch that one has to do to make it work for the general distributions.
So 2 questions. One is, eta is known for your talk?
Eta is, we can assume eta is known, but it's not necessarily. We can make it work, like we can do a binary search kind of thing.
Right. And I guess the second question was, your error guarantee seems strong. What about this? You didn't comment on the sample complexity. It seemed like for mean estimation it was n log squared n by eta squared.
Yeah.
Is that essentially optimal?
Up to log factors. Like even if you don't have any noise, that would be kind of the
eta squared, like I'm asking, because in the later slide it was eta power 4 by 3.
Oh yeah, so because we give a weaker guarantee for the unknown covariance case, so we can get away with eta power 4 over 3 instead of eta square. So
you find the smallest interval, and what defines the moment?
So find the smallest interval and consider all the points that lie inside this interval and compute the sample mean or the sample variance. That will be the estimators. So in higher dimension, there, as I alluded to before, there have been many. There are many generalizations of median. Here are 2: coordinate-wise median, where you look at n coordinate directions and compute the median in each of them. That gives you a point in n dimension. Or a geometric median, which is minimizing L2 distances. Both of these can be shown to have a square root n dependence on the dimension. In coordinate-wise median, it is easy to show that it achieves square root n by just 1D argument, because in each coordinate direction we incur an error of eta sigma, and since there are n direction, it will have a square root n dependence. So it's not just small. So both of these will achieve this bound. It's not just the lower bound. And the bad case for both of them is this, like where this is say Gaussian points. There are 1 minus eta fraction are these blue Gaussian points. And if you place all the noise points on a diagonally, that will be the worst case configuration. That will be a worst case configuration for both geometric median and coordinate-wise median. Okay, so before going into the algorithm, let's consider an easy case in the higher dimension. Suppose we are given the mean shift direction. The mean shift direction is the difference, is the direction from the true mean, the Gaussian mean, to the sample mean. Sample mean has this noise point, so it can be way off. So this is the mean shift direction. Suppose we are given this direction. Then this is an easy problem. Essentially, we can reduce it to a 1D problem. If we project all the points onto the n-1 dimensional space perpendicular to this mean shift direction, we note that there is no mean shift in this space. So we can just compute the sample mean as the estimator. And remaining is just one-dimensional problem, and in 1D everything is easy. So overall we'll incur an error of eta sigma. So if we know this direction, then the problem is easy. And one can ask if the top principal component gives this direction. But as we have seen before, even 2 points appropriately placed will completely destroy the top principal component. So that won't work. So I'll give the main algorithm. So it alternates between two kinds of steps. One is a weak outlier removal step. Things that are like really far away from the Gaussian points, you can throw them away. And then you project onto the top n/2 principal components and recurse. In the bottom n/2 principal components, we can estimate the mean by just the sample mean. Going over the algorithm more slowly, say this is our point configuration. The blue points are Gaussian and the red points are the noise points. We consider a big enough ball around the so that we preserve all the Gaussian points. So all the Gaussian points are concentrated around sigma square root n from the true mean. So it's really concentrated, and things that are, say, far away, probably bigger than 10 sigma square root n away, just throw them out. And how can we do this? We can just compute the coordinate-wise median. We know it's good up to square root n factor, and that won't hurt us for this step. So look at the coordinate-wise median. Consider a ball of, say, radius 10 sigma square root n away, 10 sigma square root n radius, and throw away all the points outside it. Okay, so then we need to identify a good subspace. What do I mean by a good subspace? It's a very high dimensional subspace where the sample mean coincides or is very close to the true mean. And we can do that by computing the covariance matrix and computing the bottom n/2 principal components. The space spanned by that is a good subspace. We can show that the sample mean is close to the true mean. So we compute the sample mean in the bottom n/2 space, and in the top n/2 space we just recurse. We repeat the whole process. So thing to note is that when we recurse, now the dimension has reduced by a factor of 2. So when we do the outlier removal step in the next iteration, the ball has shrunk because the radius of the ball is like square root n. Now it will be square root n/2. So we'll have tighter and tighter outlier removal as we progress. So here's just going over the algorithm again. We have this Gaussian points and noise points, and we consider a big enough ball, throw away all the noise points outside it, and then compute a good subspace. The property that we'll show is that if this is the mean shift vector, which is the vector connecting the true mean and the sample mean, its projection onto the bottom n/2 space is small. Okay, so sample mean is very close to the true mean. I can sketch the proof as well. It'll take 2-3 slides. So first we'll write down what the covariance matrix is in terms of the Gaussian part and the noise part. So here sigma s is the sample covariance matrix. We can write it as a sum of Gaussian covariance matrix and the noise covariance matrix, just the covariance matrix of the noise points, and rank one term coming from the difference in the mean. So what the outlier removal step gives us is a way to bound the trace of the noise points, which in turn lets us control the n over 2th eigenvalue of the sample covariance matrix. So this is just the Gaussian covariance part. If you call all the remaining terms as matrix A, the outlier removal step lets us control the trace of A by eta sigma square n. And by a standard result in matrix perturbation, you can show that the n over is called Weyls inequality. N over 2th eigenvalue of the sample covariance matrix is the top eigenvalue of the Gaussian part, which is 1 minus eta sigma square, plus the n over 2th eigenvalue of this perturbation. And because we have a control on the trace, we can say that the n over 2th eigenvalue of the sample covariance matrix is very close to that of the Gaussian part. It's just 1 plus order eta. If you just look at the Gaussian part, it is 1 minus eta. So we are just off by order eta sigma square. So how can we control the trace? Essentially, the point is that since after the outlier removal step, every point is within a distance of sigma square root n away from each other. So that essentially says that if you have a set of points that are all within a distance L from each other, then the trace of the covariance matrix will be L times n. Applying it to this will give us the trace of the covariance matrix sigma n will be just sigma square n. It's not L times n, it's just L. So we can control the trace of eta sigma n by this quantity, and the same applies for the rank 1 matrix, which is delta delta transpose. The second step is essentially that once we have a control over the n over 2th eigenvalue, the projection of the mean shift vector should be small. And why is that? So this is the mean shift vector, and look at its projection on the bottom n over 2 space. Then the Rayleigh quotient of this should be small because n over 2th we have a upper bound on the n over 2th eigenvalue. So this is essentially the argument. So if we look at the unit vector along the projection of the mean shift vector, then the Rayleigh quotient, which is this, the W transpose sigma S W, can be bounded by the n over 2th eigenvalue. And then we just argue that this can't be too big, because if this delta was too big, then it will imply that the n over 2th eigenvalue also has to be big. So what we can show is that the projection of the mean shift vector onto the bottom n over 2 space is eta square sigma square. So just to note, this is an n over 2 dimensional space, and we are incurring an error which is independent of the dimension. So this is where we reduce the dimensional dependence. And where we get this square root log n is because we recurse this algorithm log n times. So each time we have an n over 2 dimensional space where there is no dimensional dependence, but we have to add log n of this. So Combining that will give us eta square sigma square log n. So it's a pretty simple algorithm to code. This is essentially the code in MATLAB. There is one outlier removal routine that's missing here, but it's like another half a slide. And one might wonder how it does in practice. So here is a plot where we plotted geometric median. Okay, geometric median, and so this is the geometric median, which is growing with the dimension. So the dimension goes up to 2000 here, and blue is the performance of the algorithm, and the last one, yellow one, is just the sample mean, where since we know what the noise points are, we just throw away all the noise points and just compute the sample mean. In fact, I can show a demo.
A question?
Yeah?
What is eta for this?
So this is like 10%.
10%.
Yeah.
And is it just Gaussian?
This is, yeah, both are Gaussian. Spherical Gaussian, yeah. So here is a demo for just the mean estimation algorithm. Here again, so this is the geometric median that's being computed, and the dimensions go from like 200, 400, 800, and 1600. And the output of the algorithm is this blue line, which pretty much stays constant. We don't even see this square root log n. Probably square root log n is too hard to see anyway, but it looks flat. And the final, this is the sample mean, the true sample mean.
How many data points?
This one has like 10 times the dimension.
10
Yeah.
times.
What data set is this? This is
Oh, this is
the one with the worst case? Or?
this is the noise points are another Gaussian, but with a different mean. But but we tried this with many different noise distributions. In fact, Santosh gave it as an assignment to students to come up with different noise distributions, and they all plot look the same. Okay, so this one, and also let me show the covariance estimation. So the thing I want to point out is this: for covariance estimation, we actually had to compute these huge matrices. So if the problem is d-dimensional, we compute these vectors, which is d square, and we compute the covariance of this d square dimensional object. So it's like the matrices here are like d square cross d square. So the experiments I'm showing you will go only up until 60. That's something would be very good to get rid of. And there is a case where we can get rid of. So this was also in the paper. So if the problem was just to estimate the 2 norm of the covariance matrix, then we don't need to construct these d square cross d square objects. So an algorithm that we had, I won't go into detail here, is just is the following for estimating the 2 norm of the covariance matrix robustly. Is you compute the sample covariance matrix and the top principal component. And so say this is the top principal component. And we can estimate the variance also in this direction because it's a 1D problem. We can just project onto 1D. We can estimate the variance accurately. And if they are close to each other, we just output. We are done. If they differ by a lot, then we apply a threshold, 2 hyperplanes, and throw away all the points outside it. And then we repeat. So we compute the sample covariance matrix again, and top principal component, and we can show that this converges in order dimension iterations. And the key thing that I want to point out is that this constructs only D cross D covariance matrices. Though we are estimating something about a second order object, like a 2 norm of the covariance matrix, not just the mean. So it will be, so this is the threshold window. So just to summarize, we give an algorithm for estimating mean and covariance robustly, and estimating covariance matrix robustly will have many applications. In the paper, we show how it can be used for doing independent component analysis when there are arbitrary noise, small fraction of arbitrary noise. And for mean estimation, it requires only nearly linear number of samples. And you can find the code here. And there are many open questions here. One is, can we match the lower bounds in this case of unknown covariance matrix? So there was a gap of eta power 3/4 versus square root eta. Can we close that gap? Also, there's square root log n factor. And can we give a better algorithm for covariance estimation? In fact, better algorithm for either mean or covariance. But at least for mean estimation, we can easily go up to 2000 dimension equal to 2000, which is not the case for covariance estimation. And we can ask similar questions for many other learning problems where you have a generative model for generating the data. What if some fraction is chosen by, like some fraction is outlier? Can you make the algorithm more robust to such noise? Thank you.
More questions?
Very nice talk.
Thank you.
I wanted to ask, usually in practice you don't know that the covariance is spherical.
Yeah.
What do you have a technique to do that, to make the data spherical robustly?
Yeah, so we have that in the paper. So we don't need to know the covariance matrix. So if we know the covariance matrix, we can reduce it to spherical case. So when we don't know the covariance matrix, we get a weaker bound, which is eta power square root eta instead of eta power 3/4. And the main change, the algorithm is essentially the same. The main change is how do we determine this ball, the radius of the ball that we use for outlier removal. In this case, in the spherical case, we can just estimate the variance in one direction and use that as the radius. So in the non-spherical case, we can estimate the variance in n orthogonal direction. Each is a 1D problem. And that gives an estimate for the trace. And we'll use trace as the estimate for the radius of the ball. And rest of the algorithm will remain the same.
Do your bounds depend on the condition number of the covariance?
Condition number of the covariance, it doesn't, but the error guarantee will be, as I stated, the error guarantee, nothing depends on the condition number. But you can hope to get stronger error guarantees depending on the matrix. And you'll probably see that in the next talk
Is your estimate of the covariance matrix guaranteed to be positive semi-definite?
It is not guaranteed to be positive definite. We can project onto the positive semi-definite cone, yeah.
So then the error guarantee won't hold for the projected.
It will, because the Frobenius norm will just, you can show it just gets better.
Can you say a little bit more about how you put it out in the data?
Yeah, so for eta, we can try. Okay, so I should probably answer that offline because I haven't really wrote it down anywhere. So I haven't written it down. Yeah.
Does your algorithm also give some sort of approximate version of the 2K median? Did you think of the?
Yes, I think that is true. So this essentially says that you can compute 2K median approximately in this kind of average case sense. So 2-key median achieves this error guarantee, and that has to be like close to the true mean. And we show that our estimator also is close to the true mean, so that shows it's an approximation to the 2-key median. But there might be, I don't know of a way to directly compute the 2-key median, as in, it's probably not a rigorous statement. But yeah.
Okay, if there's no more, let's finish.